Today, we're going to talk about a programming language that's making a really bold promise. It claims to solve one of the oldest, most nagging problems in software development, that constant fight between safety and control. We are talking about Rust and how it's trying to give programmers the best of both worlds and maybe, just maybe, end a compromise that's been around for decades.
So, to kick things off, let me just ask you a quick question. If you had to take a guess, what do you think is the world's single most loved programming language? Now, I'm not talking about the most used. I mean the one that developers who use it are most passionate about. Any ideas?
Well, believe it or not, if you look at the massive annual survey from Stack Overflow, the answer for 5 years straight has been Rust. And that's not just a coincidence. There's something really fundamental going on that makes developers fall in love with it. To get why, you first have to understand this huge dilemma that's been at the heart of programming for a very, very long time.
Yeah, for decades, programmers have been stuck between a rock and a hard place. It's this constant trade-off. Do you build something that's super safe and reliable, or do you go for raw power, maximum control, and top-tier performance? It's always felt like you had to pick one. You just couldn't have both.
You know, on one side, you've got languages like Java. They're built for safety. They handle memory for you. They prevent all sorts of common bugs. They keep your data locked down. But then, on the other side of the ring, you have languages like C++, and they give you absolute, fine-grained control. We're talking direct hardware access, tweaking every last byte for performance. You get all this power, but it comes at a very, very steep price.
And just how steep is that price? We'll take a look at this number, 70%. That is a huge figure, and it points to a massive, expensive, real-world problem.
That's right, 70% of all the security bugs that Microsoft has to fix are caused by memory safety issues. These are the exact kind of bugs that languages like C++ are prone to. So, when you choose that path of total control, you are basically leaving the door wide open for some really catastrophic security flaws.
And this quote really just says it all, doesn't it? It captures that dream that programmers have had for ages. What if you didn't have to choose? What if you could have all that low-level control of C++ and the ironclad safety guarantees of a language like Java?
Well, this is exactly where Rust comes in. It steps onto the scene with a completely different way of looking at this old problem.
So here's Rust's secret sauce. It's all about the compiler. It lets you write that fast, powerful, low-level code you want, but it acts like the strictest proofreader you've ever met. It meticulously checks your code for all these potential safety problems, and it will flat-out refuse to compile your program until you fix them. And the key is, this all happens before your code ever gets a chance to run.
And what that promise means in the real world is you get these 3 incredible benefits. First, Rust's compiler just eliminates entire categories of memory bugs right off the bat. Second, it makes a nasty problem called data races in concurrent code impossible, again, at compile time. And third, it manages all your computer's resources automatically, but without using a slow, unpredictable garbage collector. That means you get safety and predictable performance.
Okay, so how on earth does it actually pull all this off? It sounds a bit like magic, right? Well, the magic is really 2 core concepts that are totally unique to Rust: ownership and borrowing. This is what makes everything else possible.
Let's look at a super common bug to see how this works. On the left, in C++, we create a list of numbers. We get a pointer to the second element. Then, we add a new number to the list. That simple action might force the list to resize and move somewhere else in memory, which means our original pointer is now pointing to garbage. When we try to use it, boom, we get a crash or a security hole. Now look at the right. We're trying to do the exact same thing in Rust.
And here's the difference. Instead of a bug that happens when you run the program, you get a compiler error. The program won't even build. The Rust compiler sees that you're holding a reference to an element inside the list, and then you try to change that same list. It knows that's dangerous, and it just stops you right then and there. This is the whole philosophy. Catch the error before it can ever become a problem.
This is all possible because of the first concept, ownership. It's a simple rule. Every value in Rust has a single variable that is its owner. And when that owner goes out of scope, like at the end of a function, Rust automatically cleans up the memory for you. No need to manually free memory, and no need for a garbage collector to pause your program to clean up later. It's clean, efficient, and super predictable.
But wait, if everything has just one owner, how do you actually use data in different parts of your program? Well, that's where the second concept, borrowing, comes in. You can lend out access to your data. Think of it like a library book.
You can either have many people looking at it at once, those are shared references, or you can have one person writing in it, that's a mutable reference. But you can never, ever have both at the same time. And that is the rule that stopped our bug dead in its tracks earlier.
The final piece of the puzzle is something called lifetimes. You can think of the compiler as a detective that checks to make sure no borrow ever outlives the original data it's pointing to. This completely eliminates the possibility of dangling pointers, those references to memory that's already been freed. It's another powerful guarantee that you get before your program even runs.
Now, okay, these rules are obviously very powerful, but you might be thinking, what happens when they're too strict? There are some really complex situations in programming where these rules might seem to get in the way. So what does Rust do then?
A perfect example is a classic data structure, the doubly linked list. In a list like that, every single node has to point forwards to the next one and backwards to the previous one. That sounds like it violates the one writer or many readers rule, right? So how could you possibly build something like that in Rust?
Well, Rust gives you a very carefully controlled escape hatch. It's a keyword called unsafe. When you use it, you're telling the compiler, hey, for this tiny little block of code, I know what I'm doing. Trust me. It lets you do some of those low-level, C-style memory operations. But this isn't a license to be reckless. It's a very specialized tool for a very specific job.
And that job is to build safe things for other people to use. It's a pattern. An expert programmer uses a small, contained block of unsafe code to implement some really complicated, high-performance feature. Then, they wrap that entire implementation inside a perfectly safe, easy-to-use API. So what's the result? You, the end user, get all the performance benefits without ever needing to write or even see a single line of unsafe code yourself. It's genius.
In fact, some of the most common, fundamental building blocks in Rust are built this way. That growable array vec that we saw earlier, it uses unsafe under the hood to manage its memory. Powerful tools for multithreading, like Arc for sharing data and mutex for protecting data, also rely on this exact pattern. They use a tiny, audited core of unsafe code to create rock-solid, perfectly safe tools for the rest of us.
But that brings up a good question. How can we be absolutely sure that these fundamental pieces are really as safe as they claim to be, especially if they have some unsafe code hiding inside? I mean, it's one thing to say it's safe, but it's another thing entirely to prove it.
And this is where things get really cool. Academic researchers are actually proving it. Projects like RustBelt are using hardcore computer science and formal methods to create mathematical, machine-checked proofs that Rust's safety model is sound. They're proving that it all works, even with unsafe code in the mix. So this isn't just a marketing claim. It's a foundation that's being rigorously proven, one you can actually build on with confidence.
Which really leaves us with the big question. Is this it? Is this the language that finally breaks that decades-old trade-off between safety and speed? Could it actually change how we build software in the future? Well, if the passion from the developer community is anything to go by, it just might. Thanks for diving into this with me.